Complex numbers and geometry are very well connected. In fact, if you look at a complex number z, which is sometimes written as x plus iy, you should think of it as a point x comma y in the coordinate plane. And then you can talk about its distance from the origin and the angle it makes with the x-axis and so on. Now this problem is from ISI Entrance. It says that there is a complex number z whose distance from origin is 2 unit. So this is a given information in the problem. It's a very special case. We are looking at only those complex numbers, only those points whose distance from origin is 2 unit. Okay. Create a new point P. Let's call this is a new point. A new point P, which is created by adding z with 1 over z. Now here is the catch. You should think of z as a point. This is a point. And you should also think of 1 over z as another point. And I'll tell you exactly how you can do it, how 1 over z is also a point in the coordinate plane. Now once you have 2 points, you can add them to create a third point, which is our point P. So we have all those points z whose distance from origin is 2 unit. From that you computed 1 over z, which is also a point. Then you added z with 1 over z, and this is just coordinate wise addition. So if z is x1 comma y1 and 1 over z is x2 comma y2, then their sum will be x1 plus x2 comma y1 plus y2. That's the third point. This is our point P then. Okay. All right. So what is the question? The question is, what is the path traced out by this point P? So locus of P. Find this. Find the locus of P. So if you plot all the points P in this manner, like using z and 1 over z, such that z is 2 unit away from the origin, if you plot all those points P, then what is the locus or the path traced out by the point P? This is the question. Now you can pause the video and give it a try once. There are really, let me make some space here. There are really 2 ways of doing this. 2 ways. Now the first one is very simple. You use algebra and get the answer. Do some manipulation, get the answer. And this is not hard. The second one, which is much more beautiful in my opinion, is that you use geometric imagination. Geometry plus imagination. By the way, there is a book by Hilbert called Geometry and Imagination, which is a very beautiful book, in fact. You can look into it online. Anyway, so you use geometry and imagination, and then the answer sort of appears. Answer appears in front of your eyes. So both of them are pretty beautiful, and algebra 1 is definitely, I would say, in some sense easier because it's kind of mechanical. And let's look at the algebra 1, but before that maybe I can make some space here. and make some preliminary observation. So what do we know? We know that the distance of z, here it is, maybe I can just put this thing here. Okay, so what the problem says that z, the distance of z from the origin is 2 unit. What is the algebraic significance of this fact? The algebraic significance is this, that if z is a plus ib, or which is the point a comma b, then square root of a square plus b square, that is the distance from the origin, right? If it is a comma b, then square root of a square plus b square is 2 unit. Or if you square both sides, then a square plus b square is equal to 4. This is given information. Okay, so how would you solve this naively? So if you do not have any other information, how would you sort of solve this naively? So maybe I can go to a new, check the link in the description for more interesting mathematics. Let's do this. So if we have z plus 1 over z, so z is a plus, this is a plus ib plus 1 over a plus ib, and you do something and you get the answer. So I would say don't do this. I mean, this is a very bad way of solving complex number problem. But if you don't have any other way in your, like, right in front of your eyes, then you can probably use this. This is a bad solution. There is a much more beautiful way of thinking about this. Let's quickly do this though, just for the sake of completeness. This is also something we know. This is given. Okay, so what I'll do is this is my p, right? This point is p. Okay, so this is a plus ib. Now we will rationalize in some sense. So a minus ib and a plus ib times a minus ib. So this is a plus ib plus a minus ib divided by a square plus b square, because I square is equal to -1. So you can do the computation here. Okay, so a square plus b square is 4. We know this already. So let's do this. This is equal to a plus ib plus a minus ib by 4. Now let's keep together the real parts. A plus a by 4 plus ib minus ib by 4. So this is 5a by 4 plus 3b by 4 times I. So this is the coordinate of a and b. So let me just do one thing. Let's write p here. This is equal to p. P is z plus 1 over z, right? Okay, so now what should we do with this? Well, we know that the x coordinate, let's call it px, or just let's call it x for the timing, like x naught. Maybe we can call it x naught. Okay. For this particular thing, x naught is equal to 5a by 4 and y naught is equal to 3b by 4 times I. So what can we do with this? Well, we can do a ton of stuff. We can simply, let me do one thing. Let's keep it here. Maybe we can just make it smaller here and keep this here. Okay, so what we can do is we can write a is equal to 4x naught by 5 and b is equal to, oh actually I made a mistake here. I shouldn't write I, because obviously the y coordinate is just 3b plus 3b over 4, so that's fine. Okay, so b is equal to 4y0 by 3. Okay, so now we will use the fact that a square plus b square is equal to 4. We know this, so we will use this. Let's use this right here. Okay, maybe use this right here. So a square plus b square is equal to 16x0 square by 25 plus 16y0 square by 9. Okay, but this is equal to 4, we know already. So we will complete this problem from here. So we can just divide by 4 on both sides. So we have x0 square by 25 by 4 plus y0 square by 9 by 4 equals to 1. And we know what this thing is. This is an ellipse. So z plus 1 by z is after all an ellipse. Okay. So this is simple. I mean, this can be done, but this is not the way how you should think about this problem. So let's look at the way you should actually think about this problem. What do we know? We know that z is, maybe I can actually keep this thing here, make some fresh space. We know that the distance of z from the origin is 2. So it's actually a circle, right? So maybe I can draw it here like this. So z is lying on this circle, all the points on this circle. Okay, so distance, so the radius of this circle is 2 unit. The radius of this circle is 2 unit, and the fact that z is 2 unit from origin, geometrically it means that z lies on this circle of radius 2. Now let's look at 1 over z. What can we say about 1 over z? 1 over z is the point whose distance from origin is 1 over this thing, whatever the distance of z from origin is. So 1 over 2. And its angle with x-axis is negative of the angle that z makes with x-axis. Z makes with x-axis. Okay, so basically 1 over z is somewhere here. 1 over z, this point. I told you that you should think about both z and 1 over z as points in the plane. That's how you should imagine this. So when z is here, 2 unit away from the origin, 1 over z is half unit away from the origin, and the angle, if the angle here was theta, now the angle for 1 over z is negative theta. That tells you where the point 1 over z is given the point z. Okay, so what are we trying to do? We are trying to add z and 1 over z. So we will use the parallelogram law of addition. So let's bring this picture to focus a little bit more. So we will use the parallelogram law. So let's do this of vector addition, because you're just adding 2 points. This is the origin. So we'll just complete the parallelogram, and maybe the point P, which is equal to z plus 1 over z, is here. Okay, so we have this this is one location of z. One location of z plus 1 over z. What we want to do is imagine all the locations of z plus 1 over z. How do we do it? Well, you start with this z and we will gradually push z toward this direction. We will gradually push, so maybe I can zoom a little bit more. So we want to just focus on the first quadrant. We will start with this z and we will gradually push it toward this direction. Okay, now let's do this. So start with this particular z, start with this z. This is at the point 2, 0 or 0, 2 rather, 0, 2. Then 1 over z is making an angle negative 90 degree. So z makes an angle of 90 degrees. This is z. This is z, makes an angle of 90 degree with the x-axis. This is x-axis. So 1 over z will make an angle of negative 90 degree and it will be at half distance. You should think of this entirely as a geometry problem. So this is negative half. This is 2. So if you take the vector sum of them, the point here will be at 3 by 2. Somewhere here. This is 2, 0, 2 plus 0, negative half, this point. Okay. So this is z plus 1 over z. First point. You really see the ellipse coming out of your coming in front of your eyes if you really work hard with this picture. Okay, let's do the next point. So let's draw the second z, which is here. This is another z, and let's draw the corresponding 1 over z, which is here. This is 1 over z. And we can now do the parallelogram law of vector addition. So let's do this. And here we go. Here is the point. So maybe you can do a little bit better. So this is the second point of the z plus 1 by z locus. Similarly, you can draw the third point. Let's draw the third point. You should keep on pushing this point. Maybe z is here. Just flip it and to get 1 over z, which is here. Maybe I can remove this part a little bit. And we can again do parallelogram law of vector addition and get the next point. So, if we do a little bit more carefully, let's use this a little bit here maybe, and then use this particular point. So you have the third point. So like this, you will see the ellipse coming in front of your eyes. So this will go on up to here. So you get one quadrant of the ellipse, and the same thing will be repeated in the other two quadrants, other three quadrants. And this is the final picture of P, which is equal to z plus 1 over z. It might appear to be a little bit more complicated than the algebraic method, but it's not about complication, it's about beauty. You can actually see the ellipse getting built using the parallelogram in this particular picture, which I think is much more valuable. Anyway, keep on doing great mathematics. I'll see you in the next one.